listening to Worth Electronics What's Up radio podcast, where each week we are seeing what's up in the world of electronics and PCB design. We'll be checking in with leading industry experts and our very own Worth Electronic technical specialists who are going to shine a light on our topics, such as energy harvesting, wireless power transfer, EMI issues, and so much more. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with Worth Electronics What's Up podcast. A compact and efficient design of electromagnetic interference, or EMI, input filter is one of the main challenges in high-density switching regulators, and it's critical to achieve the full benefits of electrification in automotive, enterprise, aerospace, and other highly constrained system environments. As a couple of examples here, automotive onboard chargers and also server rack power supplies. These are high power applications where it's important that the volumetric reduction of EMI filter components helps the solution fit into challenging form factors, especially with the advent of wide bandgap gallium nitride, or GaN, and silicon carbide, or SiC-based power semiconductor devices with fast switching characteristics that could potentially lead to higher common mode emissions. Common mode filters for both commercial Class A as well as residential Class B environments typically have limited Y capacitance. This is because of touch current safety requirements, and thus they require large-sized common mode chokes to achieve the requisite attenuation, ultimately resulting in filter designs with bulky, heavy, as well as expensive passive components. The deployment of active EMI filter AEF circuits enables more compact filters designs for next-generation power conversion systems. Space-constrained applications, such as those mentioned before, are ripe for even further optimization by leveraging active power supply filter integrated circuits, or ICs, to significantly reduce magnetic components and overall filter size. This podcast comes from a technical white paper created by Texas Instruments and Worth Electronic. The information frames the theoretical background and general principles of AEF circuits in terms of sensing, injection, and control techniques, with practical circuit realizations using a family of standalone AEF ICs from Texas Instruments for CM noise cancellation in single-phase and three-phase AC power systems. Measured results from a 3.3 kilowatt power factor correction, or PFC, AC to DC regulator will illustrate the benefits of EMI mitigation and board space savings. Now, as we mentioned before, common mode, or CM, EMI filters for high-density applications often have a limit to the total value of Y capacitance. This is related to touch current safety requirements. So this means that they require a large-sized CM chokes to achieve a target corner frequency or filter attenuation characteristic. The result is a compromised passive filter design. It has bulky, heavy, as well as expensive common mode chokes that dominate the overall filter size. However, active EMI filters, or AEF circuits, enable more compact filter designs for next-generation power management systems. This means that space-constrained applications can use active power supply filter ICs to reduce magnetic component and overall filter size. Ancillary benefits include lower power losses for better thermal management and higher reliability, easier mechanical and packaging designs, reduced electromagnetic coupling among components within a confined space, as well as lower cost. This image depicts the harmonic and conducted EMI frequency ranges classified by electromagnetic compatibility, or EMC, standards organizations, such as the International Electrotechnical Commission, IEC, and the Comité International Spécial des Perturbations Radioélectroniques, also known as CISPR. Applying PFC techniques enables input current harmonics to meet limits set by IEC 61000-3-2/12 at frequencies up to 2 kHz. EMI filters are still mandatory. However, in order to attenuate high-frequency noise currents and meet conducted emission specifications such as CISPR 11 for industrial and CISPR 25 for automotive applications, within classified frequency ranges beginning at 150 kilohertz. Now, as we can see in this image, only the CISPR 14-1 and the CISPR 15 product standards for household appliances and lighting applications, respectively, presently specify emission limits as low as 9 kilohertz. However, with standardization activities ongoing, the forthcoming inclusion of the 9 to 150 kilohertz band and applicable emission limits to the existing IEC 61000-6-3 generic EMI standard will surely affect the future design of EMI filters for attenuation below 150 kilohertz. EMI mitigation across wide frequency ranges require correspondingly larger passive components. Complying with EMC regulations intended to limit the levels of conducted emissions requires the insertion of a low-pass EMI filter between a switching regulator and a mains input source. This setup illustrates typical filter arrangements for single-phase, 3-wire, and 3-phase, which is 4-wire systems in kilowatt scale, grid-connected applications. L, N, and PE refer to live, neutral, and protective earth terminals. Multi-stage filters, as shown, actually provide high roll-off and are common in high-power AC lines applications, where common mode noise is often more challenging to mitigate than differential mode noise. Although this omits components for surge pulse protection and resistive discharge, the schematic does incorporate a line impedance stabilization network, also known as a LISN, in series with the input supply. This enables measurement of the total EMI, including DM and CM propagation components. At a higher level, passive EMI filters represent an intuitive, straightforward, and traditional approach to mitigate the conducted emissions of a power electronic circuit, even though the size, weight, and the cost of the passive components cause significant constraints in some applications. Such passive filter designs rely on the insertion of high-impedance series elements, such as DM inductors or CM chokes, and low-impedance shunt elements, X and Y capacitors, to create an impedance mismatch in the EMI current propagation path. The low-order switching harmonics usually dictate the size of the reactive filter components based on the required corner frequency or the multiple corner frequencies in multi-stage designs. Taking the single-phase schematic as an example, common mode chokes LCM1 and LCM2 and Y-rated capacitors CY1 to CY4 connected between the AC power lines and the earth ground provide CM attenuation. The common mode current source from the switching regulator returns first through the regulator side Y capacitors and next through the Y capacitors positioned between the common mode chokes. The alternative return path of any remaining common mode current is through the measuring impedance of the LISN setup, obviously to the detriment of the EMI performance. Now, as we mentioned at the beginning, safety regulations limit the total Y capacitance to relatively low values, often under 10 nanofarad, and the common mode inductance of the chokes required for desired corner frequency is relatively high, in the range of several millihenries, making the chokes large, heavy, and also expensive. In contrast, for differential mode attenuation, the X capacitors CX1 to CX3 could be large valued, typically around 2.2 microfarad, allowing low valued differential mode inductances using the leakage currents of the common mode chokes. As we can clearly see, common mode chokes dominate the size of the EMI filter, and they bring several challenges during the EMI filter design, including bulky volume, thermal management issues, acoustic noise, filter resonance, and electromagnetic coupling between components. In addition, parasitic elements of the filter components, especially the common mode chokes, affect high-frequency performance and achievable attenuation. The discrete components used in the filter come in different form factors from various manufacturers, and they're not optimized to fit well with each other, compromising the spatial design and the assembly of the filter implementation. In multiple publications detailing the application of AEF, results yield a substantial reduction in filter size and volume relative to the conventional passive-only design. Much like a passive EMI filter, the AEF circuit connects to the lines between the EMI source and the EMI victim. Unlike a passive filter, however, an AEF circuit uses active devices to sense the residual, either differential mode or common mode, voltage or current disturbance, and injects an imposing signal that directly negates that noise disturbance. Based on the superposition theorem of signals with equal amplitude and opposite phase, the injected voltage or current can theoretically cancel or even nullify the incident noise voltage or current contribution from the EMI source, essentially a destructive interference. This strategy is commonly applied in acoustics and successfully for EMI. So the expectation is that the AEF significantly reduces EMI, resulting in a smaller size filter versus a traditional passive-only design with equivalent attenuation. Along with AEF, other smaller passive components interface to the power stage and actually improve the overall attenuation. These circuits are known as hybrid EMI filters, or HEFs. The design and implementation of AEF and HEF circuits depend on the path of conduction, either differential mode and common mode, and the required sensing, gain, and injection stages. Now, as we can see, the cancellation signal is directly generated from a measured signal by a feedback FB or feed-forward FF approach. In this illustration, 6 active filter configurations generalized according to the sensed noise parameter, voltage, or current, the means by which the cancellation signal is injected, voltage or current, and the active control technique, either FB or FF. The term I sub S and Z sub S designate the Norton equivalent noise current source and parallel source impedance of the power stage. ZL is the load impedance at the noise receiving end, or the EMI victim. For example, the listen for EMI measurement. G represents the gain of the active circuit. Adding different passive elements in place of Z sub S and Z sub L will form different hybrid circuits. From a control standpoint, FB designs sense the residual disturbance at the EMI victim. It then inverts the signal, amplifies it with a high gain, and injects the cancellation signal back into the system to drive the sense parameter to 0 over the required frequency range. Now, in contrast, FF designs sense the disturbance at the EMI source. It then inverts the signal, amplifies it with a unity gain, and injects it back at the EMI victim. The amplifier unity gain setting for FF must be highly accurate so that the EMI and the anti-EMI signals cancel. This makes FF designs more difficult to design. In terms of noise sensing, the VS and CS elements are typically capacitors and CS transformers, or auxiliary windings on existing magnetics. In terms of noise cancellation, the VI designs use a controlled series voltage source to impede the flow of noise current to the listen, whereas CI designs involve a controlled shunt current source to reroute the flow of noise current produced by the noise source to prevent it from flowing in and then being measured by the listen. VI and CI designs effectively create a voltage divider and current divider respectively with the load. In general, transformers can embody the series element, whereas capacitors implement a shunt conduction path. This table summarizes the salient characteristics of the AEF circuits embodied in our previous picture, including expressions for insertion loss and circuit conditions for high attenuation. YS and YL represent the admittance of the noise source and load, respectively, for an FB-VSCI design. IL equals ILW/O AEF divided by ILW/AEF is the quotient of the filter output current without and with AEF installed, normally measured with 50 ohm source and load impedances, and correlates to the achievable attenuation of EMI. As we can see in this table, each AEF topology requires a specific impedance behavior to achieve high attenuation. Since magnetic components for both CS and VI are large-sized and likely custom parts, this offsets the size reduction enabled by AEF. It's a good idea to select an AEF topology that precludes the use of additional magnetic components. The VSCI implementation leverages capacitors in combination with low-voltage active circuits for sensing and injection, and thus achieves a smaller size. This image shows a simplified single-phase schematic to show the basic principle of the selected FB VSCI circuit in a common mode filter setup. Now, as we mentioned before, the main idea with this AEF topology is to use an injection capacitor with a value similar to the Y capacitance in an equivalent passive filter in order to reduce the values of the common mode chokes, which are the largest components in high-power filters. The Thevenin equivalent common mode noise source consists of voltage source Vs in series with source impedance Zs, which is considered capacitive. The mains impedance Z grid is typically inductive. Common mode chokes, designated as LCM1 and LCM2, also function as decoupling elements to achieve high source and load impedances as required for a high attenuation FB VSCI design. With Y-related sense and injection capacitors connected to the AC lines, the purpose of the circuit is to reduce the total filter volume, yet maintain low values of the low-frequency earth leakage current using an active circuit that shapes the frequency response of the injection capacitor, effectively increasing its value for high frequencies. In turn, this amplified injection capacitance over the frequency range of interest is the key to lower common mode choke inductances relative to values of a passive filter with equivalent attenuation. These are the circuit advantages. A simple filter structure with a wide operating frequency range and high stability margins. A reduced common mode choke size for lower volume, weight, power loss, and cost, while also resulting in better high-frequency performance given low choke self-parasitics and a higher self-resonant frequency. No additional magnetic components, only Y-rated sense and injection capacitors, with minimal impact to peak touch current. Enhanced safety using a low-voltage AEF IC reference to chassis ground. A standalone AEF IC that provides flexibility in terms of placement near the filter components. And also surge immunity to line voltage surges to help meet IEC 61000-4-5. Next, we'll discuss the concept of capacitive amplification. An AEF circuit for common mode noise mitigation either amplifies the apparent inductance of a common mode choke or the apparent capacitance of a Y capacitor over the frequency range of interest. A VSCI AEF configured for common mode attenuation uses an amplifier stage as a capacitive multiplier of the injection capacitor, CINJ. It is this higher value of active capacitance that supports lower values for the common mode chokes to achieve a target attenuation. This example shows that the injection capacitance is effectively multiplied by G sub AEF, the common mode voltage gain from the power lines to the amplifier output. This graph shows a simulated plot of an injection network impedance when an FB VSCI AEF circuit is enabled and disabled. The lower impedance above 2 kHz and especially above 100 kHz is caused by the capacitive amplification by the active circuit of a 4.7 nanofarad injection capacitor and its associated damping network. And here we see practical AEF implementations for common mode attenuation with an FC VSCI configuration using PSF12C1, TPSF12C1-Q1, TPSF12C3, and TPSF12C3-Q1 standalone AEF IC family in single and three-phase power systems. The sense pins of this device family interface with the power lines using a set of Y-rated sense capacitors, typically 680 picofarad, and feed into a high-pass filter and signal combiner, as we can see in this IC block diagram. The IC rejects both the line frequency, 50 or 60 Hz AC voltage, as well as differential mode disturbances, while amplifying high-frequency common mode disturbances and maintaining closed-loop stability using an external tunable damping circuit. The components between the Comp1 and Comp2 pins form a lead-leg network that sets the amplification gain characteristic. The output of the power amplifier at INJ injects the required noise-canceling signal back into the power lines through a damping and stability network and a Y-rated injection capacitor, CINJ, typically 4.7 nanofarad. The IC includes integrated filtering, compensation, and protection circuitry. The VDD bias supply ranges from 8 volts to 16 volts, nominally 12 volts, and references to system chassis ground. The X capacitors placed between the two common mode chokes effectively provide a low impedance path between the power lines from a common mode standpoint, typically up to low megahertz frequencies. This path allows current injection onto one power line, typically neutral, using only one injection capacitor. If the three-phase filter is a three-wire system without a neutral ground, the Sense 4 pin of the TPSF12C3-Q1 ties to ground, and the injection capacitor couples through an artificial star point connection of the X capacitors. And finally, we have our results. This image shows the schematic of a single-phase AEF circuit with common mode noise attenuation achieved using the TPSF12C1-Q1 active filter IC. The design includes both regulator side and grid side Y capacitors. Listen provides a suitable interface to the EMI receiver for EMI measurement from 150 kHz to 30 MHz. As we can see here, a square wave signal derived from a function generator represents a convenient source for common mode noise excitation, and a 1 nanofarad capacitor mimics a realistic common mode noise source impedance of a switching regulator. Adjusting the amplitude and transition times of the source voltage sets a suitable noise amplitude and spectral envelope measured at the listen. This simple low-voltage test with signal injection facilitates a safe and expedient performance characterization of the filter in an EMI chamber prior to connection to a switching regulator in a high-voltage operating environment. Next, we see the filter board. Using this board, we get EMI results with AEF disabled and enabled using both quasi-peak and average noise detectors. Our results show that AEF disabled and enabled using both quasi-peak and average noise detectors. AEF provides up to 30 decibels of common mode noise attenuation in the low frequency range of 100 kHz to 3 MHz, which allows a filter using 2 millihenry nanocrystalline chokes to achieve an equivalent common mode attenuation performance as a passive filter design with 2 12 millihenry chokes. In our high voltage testing, these graphs show the measured common mode EMI performance with the TPSF12C1-Q1 single phase AEF IC using the power stage of the high efficiency GaN CCM totem pole bridgeless power factor correction reference design, which is a 3.3 kilowatt single-phase bridgeless PFC converter with LMG 3410 GaN power devices switching at 100 kilohertz. We can see here that the AEF provides 50 and 30 decibels of common mode noise attenuation in the low frequency range between 150 kHz to 3 MHz, which enables a filter using 1 and 4 millihenry nanocrystalline chokes to achieve an equivalent common mode attenuation performance as a passive filter design with 2 12 millihenry chokes. To support a fair comparison, these chokes came from the same component family from Worth Electronic with a similar core material. In addition, the smaller size chokes of the AEF-based design provide better attenuation at frequencies above 10 MHz, given the lower interwinding parasitic capacitance. In this image, we can see the filters used for the EMI results mentioned before. The AEF enables a 52% reduction in box volume of the common mode chokes. This table captures the parameters for those common mode chokes. The AEF achieves a 60% total copper loss reduction at 10 ARMS, which implies lower component operating temperatures and improved capacitor lifetimes. And lastly, these impedance curves for the high common mode chokes highlight the smaller size components that have a higher self-resonant frequency and improved high-frequency performance. As an example of the higher common mode impedance at high frequencies, because of the lower intra-winding capacitance, the impedance of the grid side common mode choke at 30 MHz increases from 150 MHz to 1.1 kHz when going from 12 millihenry in the passive design to 1 millihenry in the active design. The X and O markers shown at 10 MHz and 30 MHz demarcate the respective impedances for passive and active designs. The higher choke impedance above 10 MHz for active designs largely obviates the need for grid-side Y capacitors. As expected, horizontally mounted chokes in three-phase circuits can generally yield even larger percentage footprint reductions relative to the vertically mounted chokes common in single-phase designs. In summary, recent developments in power semiconductor technology and packaging enable power supply implementations with increased efficiency and power density. However, the improved switching performance and smaller packaging that makes these gains possible is also in part responsible for elevating common mode emission signatures. The shift of next-generation power electronics toward higher densities, improved performance, reduced weight, and lower costs necessitates a new approach to EMI filter design. Within this context, a compact and efficient design for EMI filter stage is one of the key challenges in high-density switching regulator designs, particularly for automotive and industrial applications, where solution size and cost are important considerations. Practical results from an active filter implementation to suppress the measured common mode noise signature indicate a significant volumetric reduction of the common mode choke components when benchmarked against an equivalent passive-only design. Additional benefits include reduced power loss for better thermal management and increased system-level reliability, lower component weight for better mechanical robustness, improved high-frequency performance due to lower choke parasitic capacitance, and reduced costs. To view Texas Instruments reference designs along with partner events and development kits, visit Worth Electronic online at www.we-online.com/ICREF. You are listening to Worth Electronics What's Up radio podcast, where each week we are seeing what's up in the world of electronics and PCB design. We'll be checking in with leading industry experts and Worth Electronic technical specialists who will shine a light on interesting topics such as energy harvesting, wireless power transfer, EMI issues, and so much more. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with the Worth Electronics What's Up podcast.